Let me start our presentation on development of automatic voltage stabilization system for substation using deep learning. First, I will give you a brief introduction of this study, and then I will talk about proposed methods and experimental results. At the end of this presentation, I will wrap up with summary and expected contributions. In voltage control system, voltage should be maintained between the lower limit and upper limit of the rated voltage. Overvoltage or undervoltage may cause mechanical damage or experimental degradation. One of the ways to build more stable and safer voltage control system is to use reactors. Reactor is an absorber of reactive power, thus compensating high voltage transmission. If overvoltage occurs, we connect reactor to make the current voltage value decrease. On the other hand, in undervoltage situation, they disconnect reactors so that the voltage could be increased. However, most of existing voltage control system is operated by manual regulation by resident steps. It results in uncertain, inefficient, and economical voltage controls, so the necessity of automatic voltage stabilization system has increased, which would be more efficient and economic. Our goal is to develop automatic voltage stabilization system. If you look at the flowchart at the right side, our study is divided into two major parts. One is to build a model to predict optimal voltage control adjustment result, and the other is to make a user interface to visualize voltage control system. The overall concept of our proposed method is presented here. First, we developed a deep learning model to predict the amount of input required in a given situation. Although many prediction-based studies such as electric load prediction and reactive power prediction for power system stability have been presented, we thought that a new approach was needed to build an automatic voltage stabilization system. In order to build a system, the model must predict more directly, which can be the basis for manipulating power facilities. Therefore, we have the model predict the input capacity to quantify how many power facilities are needed to be used. After the required input capacity is predicted, the optimal adjustment result is derived through optimization. Optimization is the process of deciding which power facilities to preferentially select from a given input capacity by considering the operating cost of each power facility. Finally, the optimal adjustment result, which is the result of optimization, contains information of whether each of the available power facilities is operating or not. In order to predict the input capacity required to adjust the time series voltage, a model suitable for time series data processing is required. We used an RNN architecture specialized for this task to consider the time series characteristics of the input capacity and to consider additional performance and nonlinearity. The proposed input capacity prediction model is presented here. The model has an LSTM architecture in addition, by stacking two hidden layers composed of LSTM cells. More nonlinearities can be modeled. The input is composed of the path voltage and the input capacity along with the current voltage. In addition, the length of sequence data coming in as input is 4. The model predicts the currently required input capacity by sequentially processing the voltage and input capacity information of 4 time steps. The optimization formula we found is presented here. Considering that the more frequently power equipment is operated, the more likely it is to be damaged. The less frequently used power facilities should be chosen for performing voltage adjustment process. Therefore, The cost of the optimization equation is defined as the sum of the cumulative use times of the available power facilities. In addition, constraints are defined to satisfy the required input capacity. In summary, the formula makes power facilities operate as much as required input capacity, but preferentially induces operation of power facilities with fewer uses. The overall architecture of the automatic stabilization system, including the optimization process, is presented here. The stacked LSTM model processes the given sequence data to predict the required input capacity, and through the optimization process, the optimal adjustment to result is derived. Next, we will explain the user interface that can visually express the application of the modeling. This contains information on how the results of the deep learning model described above can be used in actual field. First, we define the required functions of the prototype. We need to be able to check the real-time voltage by using this. The operation of the normal reactor and the variable reactor should be automated, and information on the predicted input capacity should be provided and manual control should be possible. The following are functions that can be implemented in the UI prototype. First, it is a graph of voltage data that can be seen at the top. Pressing the green start button in the upper right corner will display the line graph of the voltage being measured in real time, allowing you to check not only the current voltage but also the trend of past voltage values. At the bottom left of it, you will see the optimal adjustment of the 5 general reactors. The green color means the use of the reactor and the red one means not use of the reactor. On the right side, a variable reactor adjustment plan that can adjust the tap step is displayed. The required tap level at the current voltage can be checked through the length of the bar graph, and at the same time, the total input capacity value appears as a white number at the end of the bar graph. Finally, at the bottom, there is a function that enables manual control. Next, we will explain the experimental results. First, the performance of the input capacity prediction model. We trained and evaluated the model with real substation voltage and input capacity data. As an evaluation metric, root mean squared error was used. We developed several models such as XGBoost and RNN and compared the performance of each model. As a result, the model performed best when the sequence voltage and input capacity composed of the past four windows were used as variables at the same time. In addition, the performance of models such as RNN specialized for processing time series data was good, and among them the stacked RNN model performed the best. Therefore, as the final model, we choose a stacked RNN that trains on sequence data. Next, we evaluate the actual operation of the system. I will explain it while watching the actual operation video. As you can see, the UI is updated at regular time intervals, and each time the voltage, the reactor adjustment plan predicted by the model, and the total input capacity are also updated. I will pause the video for a moment. Looking at the graph, a voltage of about 354 kilovolt is currently observed. At this time, the model predicted that the input capacity of 897 was required, and the reactor adjustment plan according to the optimization formula was updated on screen. The voltage that has changed since the voltage adjustment is about 348 kilovolt, which is lower than before. This is because the voltage was lowered by consuming as much reactive power as the previous dose of the reactor. In addition, the prediction is performed again for the new voltage, and it can be seen that as the voltage is lowered, it is predicted that an input capacity of about 697 is required, which is less than the previous 897. As such, the algorithm automatically predicts the required input capacity through a given voltage and performs voltage adjustment. Lastly, this is the conclusion. We thought that about the contributions of our research in two aspects. First, in terms of economy, this project can reduce uncertainty about voltage stabilization and consider the economic feasibility of power facility operation. Therefore, it will be possible to operate the power system in an efficient manner than the existing voltage adjustment method performed by humans. This, in turn, not only enables stable power supply, but can also ease the management's cost burden of increasing the lifespan of power facilities and facility failure. In addition, in terms of society, it can be used as an application case for informatization and big data in the field of substitution, and it is expected to have the possibility of development of related businesses in the future. Thank you.